Well, welcome back, everybody. And today we are moving on to a new topic, and that new topic is going to be something called binary trees. Now, I don't always teach this as a core component of the course because technically it's not part of the curriculum. It's an extension of something that we have in the curriculum. So if you're at home learning during COVID-19/coronavirus, this is considered optional content. In normal semesters, depending on the pace of the course and the caliber of the students sitting in the room, I will offer this as a regular lesson, and we will grow on our previous knowledge, which is that of linked lists. Now, so let's dig into it for those of you that are interested right now. And binary trees is a subset of an entire topic of trees within computer science. And you're going to go over all sorts of these things when you get to university or college and how they apply. But basically, they're the same idea as a linked list. They're an abstract data structure. They're a way of manipulating or managing data of any size, of any type, and working with that within a set of rules. And that set of rules allows us to do things like, for example, do really, really fast searches on data. And that's why it's important that you follow those rules. It's the same way as like the linked list structure. You're always moving in one direction if it's a regular linked list. And that rule allows us to do things like manipulations a lot easier and follow along with that. Binary trees work very similarly in the way that their structure is. So let's take a quick little review on linked lists to make sure that we're all on the same page. So we describe linked lists as a series of nodes that are connected together from one to the next in one direction. So it's very important. So looking over here, where's my pencil? There we go. So you might have one node that is then connected to the next node, which is then connected to the next node, and so on and so forth. But eventually you get to the end of the chain, and it connects to nothing. Well, that's when you know you're at the tail of the linked list, whereas the first node is the head of the linked list, right? So we have a head and tail. It just kind of daisy chains together until you get to the end. You may actually have nothing in your linked list as well, because you have another class up here, which is the actual linked list class itself, which holds one variable, which is the head, and points down into that first node. But if this first node doesn't exist at all, that basically points to null, and that means that there are no elements currently stored in that linked list, right? So that's the basics of our linked list. So every node is composed of only two things. It's composed of a link to the next node, and it's also composed of the cargo that it's maintaining, so the data that it's storing. Now, sometimes that may be as simple as just an integer. Sometimes it may be something more complex, maybe even tons of data. Who knows? It depends on what you're doing. So let's keep moving so we can carry on. This is the structure that we think of when we think of a linked list. We have that linked list class, which maintains a connection to the head, the first node. That head node then connects to the next node, which connects to the next node, and so on and so forth. And as I said, eventually you get to that end, which points to diddly squat. Nothing, nada, zip, zilch. So that means that you're at the tail or the end of your linked list. So a binary tree just kind of takes this entire idea and extends it. We just add to it a little bit. That's your UML for the linked list. I'm not going to go over that in detail. We're going to skip that. So what is a binary tree? As I said, it's another abstract data structure or abstract data type. And the idea is to maintain large collections of data, sometimes small collections, but mostly large collections of data. A binary tree is actually a special extension of linked lists, as I said. Now, linked lists, as we think about it before, has our, let's call it our head node. Our head node right here, which then connects to, look at that handwriting. Isn't that amazing? I'm going to rewrite that. Even I'm embarrassed by that. Wow. Let's try that again. Getting ahead of myself here. Not much better, but at least it's legible now. So that head node, which then connects to the next node, and we always have that next variable, which always points to that next node. Well, a binary tree also has a head, but we call it a little bit different. It's still going to use the node class, but the node class is going to have a little bit more data involved. It's still going to have cargo, and it's going to still point to some direction. In fact, it's going to point to more than one direction. So this is where, oops, I was going over here, clicking on the wrong thing. So let's talk about the binary tree. Now watch how this unfolds. We start off with one element, and that element then points to a left and a right element. So, or one node points to the left and right node. You can see why it's called a tree structure, because it branches out like a tree. Well, what do all trees have? Well, they all have a root. All right, so instead of having a head, this time we have a root structure. And instead of having a next, we actually go in two directions. So we have a left and we have a right. That's where we're going to be focusing on. And that left and right structure is what gives our binary tree all of its major properties. And how does that work? Well, basically what that means is everything on the right has a larger cargo value than the element that we're currently talking about. So if we're looking at the root right now, the element on the right over here, actually has a larger cargo value than the root itself. Then its right has a larger cargo value than it does. So the values get bigger to the right and smaller to the left. Well, what does that mean? Well, imagine if I had this scenario. Imagine if I had a root with a value of 6, and it pointed on the right to a value of 10. And maybe on the left over here we have a value of 4, because everything on the left is going to be smaller. And maybe that 10 on its right is 12. But over here, we're going to have a number less than 10. But since it's already on the right of that 6, that means that it's actually between 6 and 10. It's bigger than 6 and it's less than 10. So that means that maybe, I don't know, maybe it's an 8. That's perfectly valid. So it's to the right of 6. That's great. But it's smaller than 10, so we go left. And that's it. That's the basic rules of a binary search tree. Pardon me. There is a couple other rules, such as, number one, you can't have duplicate data. You have to have some form of tiebreaker in there. Otherwise, it won't work. The tree structure itself won't be able to find what you need, because how would it know to differentiate the two? Just going back over this. So we have our root node, and each left or right node is called a child node. When you get to the end of a tree, well, what's at the end of a tree? When you get to the end of a branch, what's at the end of a branch? A leaf. So when you get to a child node that has no left or right children, that is a leaf node. It's the endpoint of one of the paths. All right. So in this case, we see we have 4 leaf nodes. Now this is a perfectly balanced tree. What I mean like that is if there's an equal number of elements on each side. All right. So this one has an equal number. This one has an equal number. The root itself has an equal number. If I were to delete, say, for example, one of these nodes here, that breaks the balance and it's no longer a balanced binary search tree. It's very important that your binary search trees remain balanced as long as possible. Otherwise, the idea of quick searches goes away really quickly. And I'll show you examples of why that is soon. So something hidden here that sometimes is implemented is sometimes each node will also maintain a connection to its parent. Now, it doesn't have to have this, and if you're truly building a really efficient binary search tree system, you probably won't do this, because it is extra memory for that memory pointer every single step. So if you can avoid it, you should. But it does make some of the operations a lot easier, like some of the deletes and things like that. It makes life a little bit easier. Otherwise, you're kind of looking to the future as opposed to looking at where you are. But I digress. So binary trees are not always this perfect pyramid shape. That means that it's unbalanced, and we can't really get around that unless we actually shuffle the whole system. So, for example, if I have a root that started with a 6, that's great. And I said, okay, let's add in a 10. Well, a 10 is bigger than the 6, so we're going to go to the right, and we're going to add that 10 in there. And then I say, okay, let's add a 12. So, okay, let's add a 12 in there. Okay, great. And now we say, well, let's add a 4. Well, that's going to go this direction right over here, right? Now, looking at this system, it's not balanced right now. Is there a way that we can make it more balanced? Well, you got 4 elements, so you're not really got too much going on here. Let's add, say, I don't know, a 5, right? So if we had a 5 in here, well, we see a tree structure. It's definitely a tree structure, but is it balanced? Is there a better way? What if the numbers were added in a different order? So we added 6, 10, 12, 4, 5. Is there another structure that would be more balanced? Let's say, for example, if, well, this actually isn't that great of an example now that I think about it. Let's say we added a few more numbers in here. Let's say we added a, I don't know, a 9. And let's say, really break this thing, let's add a 7 as well. Right? So now let's look at this. We have 1, 2, 3, 4, 5, 6, 7 numbers in there. And the idea is that you have an equal number on each side. So you kind of want to find the median number, the number that's in direct center, and that's the ideal root, right? So if we have 4, 5, 6, 7, 9, 10, and 12, well, our ideal median number is actually that 7. And then everything on this side is going to be on the left, on the left side, and everything on this side is going to be on the right. So if we redrew this and we had a 7 in the beginning, and then the 9, great, and then the 10, and then the 12, oh, that doesn't make for a great scenario, does it? Because let's imagine if I'm searching for the 12, well, I got to go all the way through this chain. Well, again, you want to look at these, and the ideal situation is you're always finding that middle one, and that's going to be the next one. So let's cross that out for a second, and we start again. We have a 7, and that's going to go to, let's say, our 10 this time. And then we have our 9 over here, and our 12 over here. Well, that's a much more balanced system. And we do the same thing on the left side. We're not going to put the 6 next. We're going to put the 5 there. And then we have the 6, and then over here we have the 4. Now that is a balanced tree. Way better than this structure was going to be, and way better than this structure is. So you can't always control the order that you get your data in, because that will dictate the layout of your binary search tree. If I got the data in this order specifically, it would look way different. It would look like a single path. It would look like this: 4, 5, 6, 7, 9, 10, and 12. Just one single path. Doing a search through that is just like a linear search. You're just going, okay, I need the 9. Well, you got to go through that whole thing to get to the 9. If I'm looking for the 9 in this path, I go 7, 10, 9. It only takes me 3 steps. It's a lot faster, right? So sometimes, like I said, we can't control the order that we get the data in. So there's processes that we'll learn, not during this stuff, but later on, that will allow you to re-engineer the layout. And it's all just a matter of doing what I did here, is finding the median each time and making that your next element of your pieces on the left and on the right. Okay. Whew, that was a lot more detail than I planned on going. Hopefully I didn't lose anybody there. So this is your basic class diagram of your node. It's pretty much exactly the same as what we saw before in our linked list class. We have our cargo. This time, instead of just having a next node, we're going to have a left node and a right node, and potentially a parent node if you want to do that method. Here's our constructor, and we have the ability to set our cargo value, set our parent, set our left, set our right, and then the accessors for all that same data. Nothing special there. These are just accessors and modifiers for our node. Nothing really weird there. The binary tree class looks almost identical to the linked list class. The operations are very similar. So we have our count variable to keep track of how many elements we have in our binary tree. Our one node that we track of from the binary tree, which is the root node. That's it. And then that root node connects to all the other ones. So what can we do for a binary tree? Well, we can try and add. You notice that it returns a bool. The reason why it returns a bool is you might be successful, you might not be. Because remember, the simple rule that you can't have duplicates, well, if you have trying to insert a duplicate data, that's going to fail the addition. So, can't do it. Find. Find will actually retrieve the node that you're looking for based on the cargo value you're searching for. Now, that can vary depending on your implementation and what you plan on doing with it. Delete. This is the big one and the tricky one that we're going to spend some time on, is what happens when you want to delete a node. Well, looking at this structure here, it's very easy to delete this 12. You just kind of get rid of it. But what if you got to delete the 7? Oh man, what becomes the root? How? How do you make that decision? Whew. We'll get to that later. Get display list basically goes through your entire binary tree and will produce an ordered list in ascending order. Get display tree levels. Well, that does the same thing, but instead of doing it in ascending order, it actually does it by level. So we'll get 7, and then 5, then 10, then 4, 6, 9, 12. So it does it in ascending order as well as by level. And then get num children, you'll notice that's just not from the root. That is, give me a node, and I'll tell you how many children that node has, right? And all of its grandchildren and things like that. So for example, if I say, give me the number of children 7 has, I'm going to get 6. If I say, give me the number of children 5 has, I'm going to get 2. And for 4, I would get 0. Right? So it's how many children and grandchildren it has. And so on and so forth. All the way down the ancestral tree. So I just went over all those functionality. I'm not going to beat a dead horse here. We're going to keep going on that. So we'll quickly discuss the strategies here. So when we're talking about find, for example, find's a very simple process. You start looking at the root, and if the value you're looking for is bigger than the value at the node you're currently looking at, then you go to the right and check its value. If it's smaller, then you go to the left and you check its value. And you continue doing this until you either find the value or you get to a null point and you can't. That means the value doesn't exist in the binary tree. So you return either the node or a null value. Typically we return a null, and it's up to the programmer to say, oh, I didn't get anything back. That's not good. All right, so moving on. Okay. So add basically does the exact same thing. Start at the root. Okay, if the number you're trying to insert is bigger than the value that you're looking at, then go to the right. Okay, until you get to the point where, let's say, for example, I'm trying to add 13 in our list over here on the left. What's going to happen here is you're going to say, okay, 13 is bigger than 7. Okay, I'm going to go to the right. Okay, 13 is bigger than 10, so I'm going to go to the right. Okay, 13 is bigger than 12. I'm going to go to the right. Oh, there is nothing there, so I'm going to insert it as the right child of 12. Now, typically speaking, we'll do this as a preemptive check. So we'll say, if the right child, the one that we're trying to go to, does exist, then continue searching, or continue trying to find the place to add. If the right child of the thing we're trying to go to doesn't exist, that means that we're trying to go there. So set it. Quickly go through this process so you can actually see the steps. So follow the same scanning process from the root until you find a node with a null child in the direction you need to go to next. And then that's where you're actually going to insert it. Okay. I'm going to pause here because I'm going to do a separate video for delete, because delete is its own beast. Okay? Hopefully you're following along. If not, take a minute, go back over the notes real quickly, and then come back to this.